Hello guys, I'm Karthik SP from SPC and today I'm gonna video present AIML, machine learning and that is face detection. So let's start. So the first part is introduction to the face detection. Definition importance. Face detection is a computer vision technology that identifies and locates human faces with digital cameras or video frames. Its application surveillance and security. Face detection is extensively used in surveillance systems for identifying and tracking an individual in crowded areas, airports, as well as public spaces. Next is the photography. Photography application face detection helps in achieving better focus exposures as well as compositions in social media. Social media platform employs face detection for various purposes, including automatic staging of individuals in photos, creating personalized filters and effects. Facial recognition. Facial recognition serves as a precursor to the facial recognition systems and authenticates or identifies individuals based on their facial features. Next one is the emotional analysis. By detecting facial expressions, facial detection contributes to the emotional analysis. Next is the human-computer interactions. Face detection enables natural and intuitive interaction between humans and computers. Traditional approaches to the face detection, while Violajal's algorithm next was introduced in 2001 by Paul Viola and Michael Jones, one of the earliest and most widely used methods for real-time face detection. Operates by using a cascade of boost classifiers to efficiently detect faces in the images. Consists of three components: hair-like features, integral images, and ADA boost. Hair-like feature simple rectangular patterns that capture variation in pixel intensities. Next is the ADA boost is used to select a small number of critical features and to train a series of weak classifiers. Next is cascade architecture allows for fast rejection of non-face regions leading to the high speed detection speed. Next one is the traditional approach to face detection. Histogram of oriented gradients. HOG is another traditional method for object detection, including face detection included by Dalal and fixing. Emphasis on capturing local objects' appearance and shapes by computing histograms of gradient orientations. HOG operates by dividing the image into small cells, compute a gradient histogram within each cell, and then normalizing these histograms to reduce the effect of illumination changes. Histogram values are then concatenated to form a feature vector representing the entire image. Sliding window technique used to scan the image and a classifier often known as SVM is trained on these features vector to distinguish between face and non-face regions. Histogram of oriented gradients. HOG is robust to variation in lighting and pose but may struggle with occlusions and complex backgrounds. Next is the feature engineering techniques. Feature engineering involves manually designed or selecting discriminative features that captures important characteristics of faces. Commonly used faces include color information, texture descriptions, and geometrical features. Color-based features can capture skin tone and hue variations, where texture and description help in distinguishing between facial regions. Next, geometrical features such as a destination between the facial landmarks provide information about the facial structure and proportions. Next, feature engineering requires domain knowledge and experimentations to identify the most attractive features. Feature engineering techniques, while effective in certain scenarios, feature engineering may be limited in its reliance on handcrafted features which may not generalize well across different data sets or environments. Machine learning in face detection uh, support vector machines, SVM, popular supervised learning algorithm used for classification tasks from including face detection. Context of face detection, SVM learns a decision boundary that separates face images from non-face images. Features can include intensities, values, gradients, or other description derived from the image. SVM aims to find the hyperlane that maximizes the margin between different classes while minimizing classifier errors. Despite its effectiveness, SVM may require a careful selection of kernel, function, and tuning of parameters for optimal performance. Decision trees are hierarchical structures used for classification and regression trees. In face detection, decision trees recursively partition the feature space based on the learned thresholds to distinguish between face and non-face regions. Decision trees are interpretable and can handle non-linear relations between features and labels. However, they may be prone to overlifting, especially when dealing with high-dimensional feature spaces. Random forest are ensemble learning method that combines multiple decision trees to improve classification accuracy and robustness. Face detection random forest build a collection of decision trees and trained on a subset of the training data and features. During interfaces, the output of individual trees is aggregated to make final predictions. Next, can handle high dimensional data effectively known for its versatility and robustness, making them suitable for face detection tasks in various environments. The next one is the clustering techniques. Clustered algorithm groups by data points into clusters based on similarities in the features. Context of the each face detection clustering technique can be used in identifying clusters of pixel or image patches that corresponds to faces. One popular cluster algorithm for face detection is K-means, which partitions the data into K clusters based on the minimizing the within clusters sum of squares. Clustering technique may require careful selection of features, and the number of clusters may struggle within complex data distributions. The next one is the dimensionality reduction. Dimensionality reduction technique aims to produce the number of features while preserving the most relevant features in bar information. Principal component analysis widely used to dimensionality reducing technique that transforms high dimensional data into lower dimensional space while maximizing the variance. Face detection PCA can be used to reduce the dimensionality of features extracted from images, making subsequent classification or clustering features more efficient. PCA can help in reducing computational complexity and mitigating the curse of dimensionality. The next is the deep learning techniques in face detection. Architectural review CNS are a class of deep learning networks designed especially for processing structures like grid such as images. Consist of multiple layers including con- convolution layers, pooling layers, and fully connected layers. Convolution apply learnable filters to input layers, capturing local patterns and features. Pooling layers down samples the feature maps, reducing computational complexity while retaining important information. Fully connected layers aggregate features from previous layers for classification or regression tasks. Training process are trained using large datasets through the process of backpropagation and gradient descent. Another one is deep learning techniques in face detection. During training, the network learns to minimize the loss function by adjusting the weights of its parameters. Common loss functions for classification tasks include cross entropy loss. Optimization techniques such as stochastic gradient descent and variance are used to update the network parameters efficiently. Regularization techniques like dropout and weight decay are employed to prevent overfitting and improve generalizations. Transfer learning leverage knowledge gained from pre-trained models on large datasets to improve the performance of the models on the related tasks with limited data. Pre-trained models are deep neural networks trained on large-scale datasets such as ImageNet for tasks like image classification. They have learned rich hierarchical presentations of visual features which can be transferred into other tasks. Example features include VGG, ResNet, and MobileNet, which each with different traits of in terms of accuracy and computational efficiency. Next is fine-tuning strategy. Retaining the pre-trained model on a target datasets related to the task. Transfer learning process typically involves freezing some layers to retain the learned features and adjusting the weights of the remaining layers. Fine-tuning strategies vary depending upon the size of the target datasets and the similarity of the task. Techniques such as the gradual unfreezing, where layers are unfrozen sequentially, and differentially learning rates, where different features rates are applied to the different layers. Data processing in face detection. Image augmentation techniques are employed to artificially increase the diversity of the training datasets by applying various transformations. Common augmentation techniques include rotation, scaling, translation, flipping, cropping, and changes in the brightness and contrast. Augmentation helps in improving the generalization ability of the model by exposing it on the variation in the input data. Context of the face detection augmentation can simulate the real-world scenarios, making the model more robust to variations. Next is data balance techniques. Imbalanced data sets where one class is underrepresented compared to others can lead to biased models that performs poorly on minoritical classes. Data balancing techniques aim to address these issues by ensuring a more equitable distribution. Balancing the datasets helps prevent the model from being biased towards the majority class and improves stability. Normalized and standardizations. Normalized and standardized are pre-processing techniques used to rescale the pixel values of the image to a common range. Typically involves scaling pixel values to a range by dividing into maximal pixel values. Evaluation matrices in face detection. Accuracy, precision, as well as recall. Accuracy measures the overall correction of the model's prescriptions. Next, precision measures the proportion of correctly predicted positive samples. Recall measures the proportion of correctly predicted positive samples out of all actual positive samples. Next, F1 course is the harmonic mean of the precision, and recall is providing a balanced measure. ROC curve and quantitative the overall performance of the model across all possible threshold settings. Next, usage and interpretation, accuracy, precision, and recall are commonly used matrices for evaluating face detection models. F1 covers provides a single value that balances precision and recall, making it useful for comparison model and selecting. Next, challenges and limitations in face detection. Occlusions occurs when a part of the face is obstructed by objects, hands off, accessories, or peop- other people in the scene. Occlusion poses a significant challenge to the face detection algorithm, as they may fall to the detect faces with crucial facial features or hidden partially covered. Common approaches to address confusion include multi-view face detectors, which face detects from different angles, and leveraging context information. Pose variation refers to the changes in the orientation of viewpoint to the face in the scene. Illumination changes occurs due to the variation in lighting conditions such as shadow, reflection, or direct sunlight. Next is addressing multiple challenges. Many face detection systems employ a combination of techniques to address multiple challenges simultaneously. Transfer learning technique where pre-trained models are fine-tuned on specific datasets or tasks. Conclusion addresses the challenges and limitations in face detecting requires a combination of algorithm advancement and augmentation techniques, risk-processing methods and optimization strategies. Reactive advances in face detection in hardware and algorithm have led to significant improvement in real-time face detection. Uh, for deployment on edge devices in the source-constrained environments, recent advances in face detection. Edge computing refers to the parameters of processing locally to an edge devices rather than relying on solely piracy concerns as well as ethical implementations. Detection technology becomes more pervasive when there is growing concerns about its potential impact and civil liberties. Piracy concerns and ethical implications, including fairness, accountability, and transparency, and gaining attention in the development deployment of face detection systems. Future directions, such as advances collaborative efforts, as well as future research in the face detection. Recent advances in face detections increase demand for the real-time application. These model leverage optimization, efficient model architecture, as well as real-time face detection as application dimension, surveillance, augmented reality, robotics, etc. Reactive advances in face detection, edge computing recent advances enhance reliability as well as edge-to-cloud collaborations. Privacy concerns and ethical implications. Face detection involves becomes more prevalent. Privacy concerns arise from the potential misuse of the facial recognition. Ethical considerations include related to the bias and fairness in the face detections. Privacy concerns and ethical implications. There is increasingly emphasis on the regulatory frameworks and guidelines to the government responsible of use of the face detection technology. Case studies and applications. Overview application benefits, efficient monitoring. Case study and applications by analyzing pattern on movement and behavior captured by smart cameras. Retail store uses smart cameras with face detection to monitor traffic and detect shoplifting incidents. So this is the conclusion part. Emotional analysis by detecting facial expressions. Detecting contributes to the emotional analysis systems that interfere to the emotional state of values of the individuals, as well as human-computer interaction in intuitive interaction between humans and computers. In conclusion, DTEX plays a pivotal role in various domains from security and surveillance to the environment as well as healthcare. Techniques, challenges, and recent advances in the face detection through representation. Summary, traditional approaches, machine learning, deep learning, as well as data processing techniques for future research and development. As technology continues to evolve, there is a need for future research and developing in face detection to address emerging challenges and opportunities. Summary of key points, evaluation methods in accuracy, precision, and recall. Recent advances in real-time face detection. Future directions include multi-modal approaches enhancing robustness and generalization. Importance of face detection in modern applications serves as a foundational technology in various modern, including surveillance, security, human-computer interactions. So this is the end of this slide. Thank you. Have a nice day.